Alright, so yesterday, by 2 minutes, it's almost January 3rd, middle of the day, January 1st, I came up with a design for an abacus that can handle algebraic equations. Just an entire algebraic equation handled with one, well, it's like a cluster of abacuses. And basically a die that indicates your comparators. So, see, equals, and I have it this way, one, because the tool that I had to paint with was just a stick, and I'm not going out of my way to figure out how to make fancy little designs, but also this is symmetrical either way we look at it. So if I'm looking at it so that I can see it this way and you can see it that way, hey, that's nice. So we've got a comparator, so that's equals here. This side is going to be greater than this side, so that's what that indicates. The 2 is more than 1, so whatever's over here is less than whatever's over here. Then this just goes the other way, and that's an equals. So we can just kind of rotate through our options real easy, right? To go between equals or greater than or less than or whatever. Alright, and now these guys, the way that they're working is, my hand keeps blocking all of the light. Let's see, that doesn't help. Whatever. So this whole thing, this is a little base 3 abacus. So each one of these units, so there's that little white dot, and then there's a face on either side that's black, and then we get red, and there's a white dot, and this red white dot is exactly opposite the black white dot. Like, right, they're exactly opposite each other. Red indicates negative, black indicates positive, and these are just bolt with nuts on it. So these end up being ternary bits. So you've got, so if a blank side is up, doesn't matter what color it is, that's a 0. If a red 1 is up, that's a 1, or that's a negative 1. If a black 1 is up, that's a positive 1. And this is a base 3 polynomial. So right next to, this is the unit. So we can have blank indicates it's a constant. 1 dot indicates that's our first variable. 2 dots is our second variable. And again, this is, no matter how you are viewing this, you can read it. So it's a little bit nicer than maybe X or Y, and you could use this to represent equations where maybe X and Y are not your variables, it's something else. So yeah, that indicates your unit, and just like here, the antipode of the 1 dot is 1 dot, the antipode of the constant is the constant, 2 dots is its own opposite. So what ends up happening, the nice thing here, let's set a number here. So this will be, let's do it in terms of X. Let's do that. So we've got, our variable is X. This is a negative 1, this is a positive 3, so that gives us a 2. This is a 9, so 9 plus 2, this would be 11x. So we set that down, so we'll say 11x is equal to, sure, this one's already set up as 1y. So 11x equals y. And it doesn't really matter how these are oriented. You could have it something like that. It's still, because this is your 0 power, first power, second power, third power of the 3. That's how it works. Let's see. I think there's better light if I move it over this way. It's slightly more awkward to me. It feels like it should be worse, but it's actually better, I think. There we go. Alright, so we've got negative 1 times 3 to the 0 power, 1, positive 1, times 3 to the first power, positive 1 times 3 squared, 0 times 3 to the fourth. Right? Doing this, we can get magnitudes up to 40. If you added 2 more bolts, you could get up to 364, which I feel like that's a decent standard to put it at, because it's not going to be too big. If you could actually still use it with a system this size, but now it's big enough to handle computation over like a calendar. It's very convenient. Okay, so now let's say we want to move this guy to this side of the equation. Okay. Classically, if you were writing it out, you would like subtract from both sides, and right. Watch this. So this is the one we're moving. I'm just gonna pick it up. I'm gonna grab it so that I have control over it really nicely, and I'm just gonna flip it over, bring it to the other side. There you go. I just did that operation. So these two terms is the same as 0, because this equals this, right? So this is 11x is 1y. So if we take the y, we flip it over, bring it over to this side, now we've got negative y plus 11x is nothing. Boom. Beautiful. You can see from this that addition and subtraction are not operations. I didn't subtract anything anywhere. All I did was this. Move that over. Boom. Negative y plus 11x equals 0. $11x equals y. Zero equals y minus 11x. So, and then we can do, let's see, from the camera's point of view, I don't know, whatever, I'll just do it from my point of view. So I've got, I actually prefer looking at it this way. So now I've got y equals negative 11x. Let's do plus 4. Let's set that to a constant. There we go. So now it's like a standard linear equation, right? The slope-intercept form, right? We've got y equals negative 11x plus 4. Or, that's 2. Plus 2. I swear I know what I'm doing. Y equals negative 11x plus 2. Okay? If we want to take that constant, flip it to the other side. There we go. We've got negative 2 plus y. Or we can swap these around and get y minus 2 equals negative 11x. Or we can bring this over here. Make sure I don't jack it up. I jacked it up. There we go. So we've got (11x) negative 2 positive y. Just bring all this over here. There we go. Negative 2 11x equals negative y. Negative y equals 11x minus 2. Right? You can play with the equation, manipulate it however you want. The terms are just automatically single units. We can find the additive inverse by just flipping it over as we cross the comparator. You can have different comparators. It can be equals. It can be this is see, this is now bigger than this. This is now bigger than this. Equal, bigger, bigger, equal. Boom. If you wanted to do like y squared, we could take another one of these nuts and put it on there and have them both set to y. So, but you could also like set it to x. So you could have something times xy. So we can do pretty much any elliptic function exactly as you would write it. And you can manipulate it insofar as you can manipulate elliptic functions. Or, you know, you could deal with a quadratic. There's enough pieces here to do a quadratic. We could do, right? We can handle point slope form of a linear function, standard form of a linear function, and slope intercept form of a linear function with just this, with what's here, with these four. As long as you only have like one fraction in there, which is pretty common if we were looking at like middle school and high school questions with this. It's pretty common that you're really only going to have a fraction on the x coefficient. And if you wanted to indicate that this way. So for me, it literally looks like a fraction. So I've got, let's see, I'll try to make it so that it looks like that for the camera. And let's give this a more interesting number. Let's give it like a 3. So now we've got 11 on 3 times x. And you could say, well, let's make it x on y. Right? So this is now x divided by y. 11x divided by 3y. Right? We can do really interesting things with this. And all because we just recognize that subtraction is abelian. And how equations actually fucking work. That's all it took. And now you have these like manipulative versions of equations that you couldn't do before. Positive y. If I just flip it over, negative y. There's better ways to do this. There we go. This one, we can move it over here. This we can move over here. It's kind of off camera now, but I can just slide everything over so that it's nice and visible. There you go. A better way to do an abacus.